Today, we're going to do some new stuff, some new things. So I want to give a little bit of an introduction to flocculation, and then I want to have an opportunity where you all think about flocculation. When we ended the last time, we had just figured out that that things like bacteria cells would settle at ridiculously slow velocities, and I just wanted to like drive that point home, that there's a reason why we are planning on flocculating the water before we send it to our sedimentation tanks. And that is, if you were waiting for a bacteria cell to settle, you would need a sedimentation tank that is on the order of 100,000 times larger than the sedimentation tanks that Agua Clara builds, which would mean that they would cost on the order of 100,000 times more. And that would mean that if you were thinking about building one of these in Tanzania, you would say, I guess not. Whenever you see factors of 10, let alone 100 or 100,000, like, it's a big deal. A factor of 10 is a huge thing. And if that's not clear to you, think of it in terms of the hourly rate that you would like to earn. And if a factor of 10 doesn't get you excited, well, then I don't know. I guess I ran out of ideas. But most of us would get excited about a factor of 10 with a salary bump. So we've got to figure out this factor of 100,000, that if we want to remove bacteria in a sedimentation tank, and we will end up successfully removing bacteria in a sedimentation tank, we've got to figure out the trick. And the trick was, and you saw that with this slide, that if we could increase the diameter of the particles by maybe aggregating them, bringing them together, we could get them to settle faster. So that's what we're on the path to do. And let's see if this works. This should be the audio. I'm curious here, do you hear the audio?
Process in which particles collide and stick together to form snowflake-like fractals called flocks. Flocks are easier to remove from the water than individual particles because they have larger diameters and therefore settle faster in the sedimentation tank. To facilitate flocculation, a sticky substance called a coagulant is added to the water. Coagulant nanoparticles coat the surface of particles and act like glue. The most common coagulant used in Agua Clara plants is polyaluminum chloride, also known as PAC. The coagulant dose is determined by the chemical dose controller, as previously mentioned. The flocculator consists of a concrete channel segmented by large plastic sheets called baffles. The baffles are staggered across the top and the bottom of the flocculator, forcing the water to flow in a vertical zigzag pattern. The baffles in the flocculator create fluid deformations by repeatedly forcing the flow of the water to change directions. These fluid deformations cause particles to collide, and their coagulant coating sticks them together to form flocks. Pieces of pipe attached between the baffles creates additional fluid deformation by obstructing the flow of water. The flocks travel to the end of the flocculator, where they enter the influent channel of the sedimentation tank.
Okay, so flocculation is a process where we create some conditions so that particles can attach to each other and grow larger. It requires two things. It requires transport, meaning that particles that are separated by some distance in the fluid have to somehow get closer together, hit each other, and somehow where they hit, they have to be sticky so that they stay attached. So we're going to cover the attachment part next, and then we'll talk about transport as a following step, and that's where you'll come in. So the first thing is that the goal of flocculation is to have all the particles attached to each other and form flocks that settle faster. So the goal is to not have any primary or original particles that have not yet attached to anything. The goal is to not have any primary particles that are left. Everything should have attached to something else. So our goal is to reduce as much as we can the concentration of particles that have not aggregated. So some definitions. A coagulant or coagulation is the process of adding the sticky phase material. You said and I call them adhesive nanoparticles. They are nanoparticles. And they're going to attach to the particles that are present in water, the bacteria cells, the clay particles, cryptosporidium, all those things that we really don't want in our water, so that when those particles touch other particles, there's a chance that they will stick together. So first, these blue dots are the coagulant nanoparticles. And the first step is to get those coagulant nanoparticles on the particles that we're trying to remove. And then the next step is flocculation, where we produce collisions between the particles. And the goal now is to have collisions happen where two particles hit. At the point of contact, it's sticky, and so they attach to each other and they aggregate into this larger particle, or which we call a flock. So I'm going to go through this quickly, and you can have it as a reference. First coagulant that is commonly used is alum. It's aluminum sulfate. It's got a bunch of waters on it. You can buy it as this granular material, or you can buy it as a liquid. If you buy it as a granular material, it looks a lot like road salt. It's very widely used. And let's skip to the bottom of this slide. When you add aluminum sulfate to water, it disassociates, the sulfate comes off the same way that the sulfate would come off if you added sulfuric acid to water. It would dissociate and produce acid, the protons. The same thing happens here. The sulfate comes off the aluminum, and then hydroxides come on and join the aluminum. And those hydroxides got there by leaving water molecules. And when they left the water molecule, they left a proton behind. So you end up with lots of protons in the water that you didn't have before. So I don't know how chemistry is, but it's one of those cool things. And it explains what's happening here. So we're adding, essentially, when we add aluminum sulfate to water, a bunch of protons show up in water, H pluses. That means that we're increasing the concentration of those hydrogen ions. And that means that the pH is dropping. So this is just a reminder that pH is just the negative log of the hydrogen ion concentration. We're increasing H plus, so that means the negative log of that is decreasing. And so we're ending up with a lower pH. So acidic, lower pH. So that's one important thing to remember about adding a coagulant, especially alum, that when you add it, the pH drops. And a natural water that has been, out there in the environment, in a stream, maybe it was flowing over some limestone and it was dissolving some calcium carbonate as it went down the stream, or as it went through the farmer's fields before it got to the stream. That calcium carbonate is essentially like a base that's in the water. And so that base can neutralize the alum when we add it so that the pH doesn't drop too much. But if we add so much alum that it has basically reacted with all the base that's already in the water, then the pH can drop quickly. And if the pH drops too far, then the alum that we add no longer precipitates, and instead it stays in solution. Now, can you think of a problem if we have this, we're adding this coagulant and we're thinking of it as a glue, like it's a glue, it's sticky. And if it's not solid phase, what do you think about that? What do you think about a glue that is liquid? Would a glue that is liquid hold things together? By the way, what's the definition of a liquid? You might have remembered this from fluid mechanics. In a liquid, if you apply a stress to it, what does it do? Anybody remember? If you apply a stress to a liquid, for example, if you drop a cannonball in water, that gravity is pulling on that cannonball. Will the cannonball just go into the water a little bit and then stop? No, it just keeps on going. So if you have a glue that is liquid, it has no ability to stop continuous deformation. A liquid, by definition, deforms continuously when you apply a force to it. So that means that if we add a coagulant and it doesn't switch to the solid phase and it remains in the liquid phase, it's worthless as a glue. So what's the take home here? If you add a lot of coagulant and the pH drops and the coagulant no longer precipitates into solid phase, the coagulant won't work. So if you add too much alum to a water so that the pH drops, flocculation will fail, guaranteed. So now you know, you can make flocculation fail by adding too much coagulant. You're adding too much glue and the glue is no longer sticky because it's no longer in solid phase. There's another coagulant that is commonly used. It's called PAC, or polyaluminum chloride. It's the one that Luke Meyer mentioned in the video that we just watched. And it's also got aluminum in it, which is pretty important. It's got aluminum in it, and it was slowly titrated in the factory to make it less acidic. So it's like partially neutralized already. And that means that when you add PAC to water, it doesn't cause the pH to drop as much. Or you can use more of it before you would run into trouble with having the pH drop and it failing to precipitate. So it's less acidic, and almost all of the water treatment plants that we're working with in Honduras have switched to PAC, and many of the water treatment plants in the United States have switched to PAC as well. It is at least in many, many cases, it works better than alum. So given the option, it's a better option. It's easier to use because of this pH issue. So that's FYI about how acidic the PAC is. The take home is that in either case, you end up having this aluminum hydroxide that is precipitating and forming these sticky nanoparticles. And I'm driving home this point about solubility. Like you could say, oh, well, why can't I add NaOH or calcium hydroxide to water? Well, the reason that those don't do it, or at least one of the reasons why those don't do anything for us, is because those are completely soluble at neutral pH. So they have no chance of working. The coagulant has to be solid phase at neutral pH in order for it to actually do its work of gluing particles together. Another cool thing about aluminum hydroxide, these nanoparticles, they are sticky. We kind of hold that question lightly about why are they sticky. We have hypotheses that it's because aluminum hydroxide is very, very, very polar, even more polar than water. And so that may be one of the big reasons why it is sticky, but that is something that we don't have well defined. But we do know that aluminum hydroxide is so sticky, it likes to stick to itself, it likes to stick to lots of different kinds of particles, and that's why flocculation using these aluminum-based products has been working for the last 100+ years. And I think I failed to mention in this presentation, another coagulant is ferric chloride. And it's interesting, it's Fe+3, just like it's Al+3. So when it precipitates, it's going to grab 3 hydroxides around it. It has very similar properties, iron hydroxide and aluminum hydroxide. Both of them end up forming these sticky nanoparticles. I have no experience using iron as a coagulant, but I know that it is done in some plants. So we're seeking these attachments between particles. We're going to add this sticky insoluble coagulant. Just a little aside here. What other coagulants have you heard of? Has anyone heard of something else that you could use as a coagulant? Possibly not. It depends which circles you run around in. Okay, so another coagulant that's out there is there's a moringa seed. It is a plant that grows in many parts of the world. And anytime I get a group of students working on water treatment, someone says, well, why don't we switch to moringa seed as an alternative coagulant? It is a possibility. I am exceedingly skeptical that it would work for a number of reasons. One is I've noticed that no water treatment plants in the United States are switching to moringa. And so I'm guessing that there's something that is catching people and making them be reluctant to make a switch to moringa seed. It would take a lot of moringa seed. It requires developing a method to have it work in your chemical dosing system. Oh, and here's another really key insight. Polyaluminum chloride and alum, when you add it to a little bit of water and make a concentrated stock solution, it's completely soluble. Why? It's because of what I told you earlier. When you add a lot, it drops the pH. pH goes low enough that it no longer precipitates. So the aluminum hydroxide solutions, whether they're made by PAC or alum, are these lovely thick solutions that you can run through our dosing system, and it works just fine and it doesn't clog it up. And then it adds to the water, and when you add it to the water going through the plant, it dilutes so much that the pH is now close to neutral. The nanoparticles precipitate, or the aluminum hydroxide precipitates, forms the nanoparticles, and we have our glue. So if you were trying to use the moringa seed, the challenge would be that it's, I'm guessing, always insoluble. And so you would have the fun of figuring out how to dose it in a water treatment plant. The agua-claret doser that we have that is good for dosing liquids wouldn't work. And then there's one more reason, and that is you've just added an organic to the water, and we keep on hitting this issue that if at the end of the process, we're hoping to add chlorine, and chlorine reacts with anything that's organic in the water. And so if there's any leftover moringa seed organics in the water at the end of the process, they're going to react with the chlorine and cause us problems. So we're really happy with the alum coagulant because it doesn't have any reactions with the chlorine, and most natural waters are already exposed to aluminum. There's aluminum everywhere in the environment. It's, I think, the second most common element. Check me on that. You can Google that real quick. It's one of the most common elements in the Earth's crust. And so that means that it's everywhere. The water already is in equilibrium with it. We add some more, and then we remove the excess, everything that precipitates out, we remove that in the plant. And so there's similar levels of aluminum leaving the plant as what entered the plant, because there was already aluminum in the water that entered the plant. Okay, so that was my aside about moringa seed and why we're not using that in any of our plants yet. I'd like to give you a sense of the scale of the particles that we're trying to remove. So we're talking about nanoparticles that are made of aluminum hydroxide. We're talking about eventually dissolved organic molecules, like there's humics and there's tannins and there's water, that there's chemicals that come from the rotting of the forest vegetation, the leaves, and those form tannins and humic substances, and those end up making the water have this tea color. And those molecules are actually fairly large, and they end up interacting with our coagulant as well. Then there's inorganic particles like clay. They might be like platelets, like plates. They probably are not round, but I was lazy and made it round. And then there are bacteria and other organic particles that we'd like to remove. And to think about scale, there's a human hair that's, there's an error on this slide. My hair is not 50 millimeters in diameter, not usually. I usually don't have to get out my sawzall to cut through my hair. That would just be awkward. So that was supposed to be a micrometer, 50 micrometers in diameter. A factor, this is another case where a factor of 1,000 does make a big difference. So that was 50 micrometers. And then I tried to make things to scale on this slide. So there's a clay particle. It's only about 5 micrometers in diameter. There's a tiny little bacteria cell. And I don't know, you probably can't see the coagulant nanoparticle, but it's kind of like the smallest thing that you could imagine on this screen, like 1 pixel or less. So these are the sizes, roughly. So if you want to think about it in nanometers, a clay particle is 7,000 nanometers or 7 micrometers, roughly. Bacteria is 1,000 nanometers or 1 micrometer. And then the natural organic matter might be 50 nanometers in diameter. And some of the chemists might argue about whether all of these things are in solution or whether they are in suspension. And that line is kind of arbitrary and capricious. They all have some particle-like behaviors, even natural organic matter, which can act like it's completely dissolved. It also has some particle-like behaviors when it has a chance of attaching to a coagulant nanoparticle.